this. So this is the culminating lesson, lessons 8 and 9 in our textbook, because next week we're going to focus on some Khan Academy, some digital resources to really work with, furthering our comprehension of the unit circle and SOHCAHTOA, our right triangle trigonometry, which basically kind of reiterates my point. And sorry if you can hear those sirens in the background. Reiterates my point that this is the last time that we're going to be working with our virtual textbook, since y'all don't have the hard copy of it, but that's awesome. So it's kind of cool little milestone that we're passing today. So nonetheless, let's get to business here. Let me make sure. I know with the whole app update, we kind of dealt with this on Tuesday, but hopefully y'all can see my screen. If at any point you can't see the announcements that are about to go up, let me know by either unmuting yourself or typing in the chat. Y'all know the drill. So same old, RLA, RLQs, follow the agenda, let me know about the questionnaires. Please feel free to do that anytime. Ed puzzles and assignments with the flexible finish line, the new updated finish line due by next Friday. Office hours tomorrow at 11 a.m. Hopefully you all saw the FAQ and info sheet, gave us some information about why the, or rather that kind of reiterated that Friday, May 22nd deadline, what that optional project is going to be about, no final, all that good stuff. And a lot of you have been doing a really good job asking these questions to me in that Google form. So hopefully I've been able to respond to you. If you sent out or commented on that Google form and I haven't directly reached back to you on an email, please email me again or let me know, okay? So I just want to make sure I get all of your questions, comments, or concerns answered. And that takes us to number 5, that year-end form. As of starting this, I had like more than a third of you filling that out. So actually, I think it was half of you filling it out in my Algebra 2 classes, so good job. If you haven't done it, please fill it out. It was posted in today's announcement, and that's how you got into the Zoom session. And that's what the optional final project is all about. So really T-minus 3 weeks in terms of the flexible finish line, if you don't want to do the project, is really now T-minus 1 week and today. So after this class session today and your work tomorrow, you really only have 1 week left, and that's where that 5/22 finish line comes for our assignments and ed puzzles, again, if you're choosing to not do the final project. All right, I'm cruising through the announcements, trying to get through it relatively quickly today. Awesome. So that way we can practice what we have learned through the completion of assigned problems. That's our goal today. And what I mean by that is really finish up the lesson 8 homework and try to get as much as we can on lesson 9 homework. And if you see on the left side of the screen there in the purple box, the pages 129 through 132, that top bolded number section, that's our lesson 8 homework. And 141 through 143, that is your assigned homework for lesson 9. That is our goal today, trying to really get those assignments understood and comprehended, but also take this opportunity together to work on it together so we can really feel comfortable with that material. So if anyone has any questions, now would be a fantastic time to kind of shout out and let me know, or type it in the Zoom box. If not, I'm going to move right into our material for today. All right, cool. So on Tuesday, we completed this problem, which is on page 129. It was in lesson 8, problem number 5. We were working with, in this problem, a Ferris wheel that had a 40-foot diameter, whether it be from side to side, top to bottom, or diagonally. The distance across the circle was 40 feet. And then we were able to, over here on the left side, and yeah, awesome. I think we can maybe all see that. Let me zoom out a little bit, and just in the off chance that we can't. We created this function, this kind of wave-like, curve-like function based off of the fact that we started, or the bottom of this car was 2 feet off the ground, and at any given quadrantal angle, the big 4 angles, 90, 180, 270, and 360, we were basically oscillating, meaning moving up or down in increments of 20 feet, because if the diameter is 40 feet, the radius was 20. So if you were here on Tuesday, that was a complete reiteration of what you heard. If not, that was kind of where this information came from and how we started 5A. Now, again, I wanted to do the rest of this homework, so really I wanted to focus our attention now on 5B and basically use that graph that we created right at the top of our screen right now to mainly talk about the domain and the range. So for this sake, I'm going to use some different colors here to describe the domain and the range independently. From our work in this class, we know the domain is all the x values. So thus, if we're talking about this Ferris wheel, sorry about that, this Ferris wheel going in one cycle, one full rotation, the domain is basically going to be the degree of rotation, since that's our x-axis at the start, 0 degrees. So the domain is basically going to be from 0, and that's our x value, all the way up to the farthest right value in one whole circle. Any revolution, one full circle is a full 360. That's our domain, from 0 to 360 degrees rotation. What's the range? Well, the range is all the y values. So if we were to look up at that graph on top, we see that basically the lowest point is here. And, not to scale on this graph very well because I drew it by hand and we all know what that looks like on this whiteboard, but the lowest point of this Ferris wheel, if it's lifted 2 feet off the ground, the lowest point would have to be at this height of 2 feet. And it can be equal to 2 feet, hence the less than or equal to. So y is everything at 2 feet or above it. And then the highest point on this Ferris wheel was right up here, which was 40 feet above 2 feet, aka our highest point on the wave over on our function on the coordinate plane that we graphed on the right here, number 5, would have been 42 feet. So in layman's terms, or in common speak, the domain is basically saying, hey, between 0 and 360 degrees on this Ferris wheel, you would be at a minimum height of 2 at any given time, and the highest you'd be off the ground would be 42 feet at any given time. Cool. Hopefully we're kind of feeling comfortable with that concept. And now all that we're going to do is basically reiterate this graph up ahead as my screen awkwardly scrolls down really slowly. It's lagging. We're basically going to recreate this graph here, this wave-like motion, this sinusoidal function, as we're kind of getting introduced to it as in this class. But now we're going to do so if you were to, say, start at the top of the wheel for one turn. So I'm actually going to call on someone. If you guys could help me out on this, either through chat box or out loud, I would love to hear your voices. Can anyone tell me if we started at the top of that graph or at the top of that Ferris wheel, where our height would be at the start? Again, you could type it in if you're up for it. If we started at the top of the Ferris wheel at 0 degrees, what would our height be? And I know, don't be shy. You can type it in that chat box. All I'm looking for is a number. Y'all know I'll wait. As a matter of fact, to kind of kill the silence as I'm waiting for an answer, and any answer is fine. I've been working a lot on breath work and trying to really center my focus here as this quarantine's going on, so I could take this moment and really focus on just chilling and meditating, so to speak. So I'll be patient.
Can you repeat the question? I'm sorry.
Yeah, no worries, no worries. So if we were to start at the top of the wheel, where would our height be at the starting point? So like instead of starting here, if you were to somehow be able to start your rotation before like the ride turns, if you've ever been on a Ferris wheel, like you were right up here at the top, at the start of the ride, where would your height be at that moment?
Isn't it just 42?
Yeah, that's all I was looking for. Thank you. Right on. Cool, 42 feet. So that's going to be our y-intercept. That's our starting point. And then effectively we're making 90-degree rotations as the following. So after 90 degrees, boom, we're now down at this height here, which we know is basically a radius below 42. So now we're back down to 22. Sweet. At 180 degrees, we've made it all the way down to the bottom, which is at 2 feet. at 270. Sweet, we're now back the same height as we were at the 90-degree rotation. So at the 90-degree rotation, we were at 22 feet, 270, we're back there. And as a full circle, we're back to where we started at 42. And there is our curve-like motion. Again, the unhinging of the circle. Sweet. Hey, thank you. Unfortunately, I didn't see who that was, but shout out to
It
whoever.
was me.
Thanks, Sam.
No problem.
Appreciate it. Okay, shout out to you, Sam. I'm sure if you're watching this on YouTube, you're probably gonna be laughing at my awkward faces. I was sitting there waiting. But awesome, we are there on the curve. So there's our curve for 6A. So basically, again, same thing. I'm just actually going to copy and paste the work here that we did on 5B because it's really saying the same information. All right, now again, our domain is still between, you can see down here at our x-axis, 0 and 360. And our height is still between a max value of 42, we just started there, and a min value of 2. So really the domain and range are identical there. The nice thing about me doing this on an iPad is I can copy and paste. If you're doing this on a piece of paper, unfortunately, you don't have that luxury, but it is really the same answer. So does anyone need me to stick on this page here at the bottom of 129? Again, this is lesson 8, problem 6. As y'all write this down or copy that down. All right, here we go. Then let's move on down to number 7. Describe how the graph of the function in problem 5 would change if you sketch the graph for 2 turns. So basically what this is saying is instead of, we started at on number 5, here's our circle again, really poor drawing, but y'all get the idea hopefully. On problem number 5, we started at a height of 22 feet. Up here we got at a height here, I guess we could just do this, give us a little bit better idea. We started at 22 feet, we eventually got up to 42 feet. As we turned, we got back to 22 feet on that quadrantal angle, a full 180. Then down here, we were at a height of 2 feet because our radius had gone down. And once we made a full revolution, we were back to 360, which resulted in this graph. Okay, for a real rough sketch. That was basically what it resulted in, and you know what, maybe I should be better and put that right on the x-axis. Cool. So basically what we're now asking is what would happen if you graphed it for 2 turns? Well, for 2 turns, basically what we would do is we would just take this very same graph, by the way, and just repeat it, because the reality of the situation is if you go around a second turn on the Ferris wheel, it's not like you can get any higher or lower than you were originally. You're going to only be at the same max or min height, as I do a very poor job tracing, kind of hard to see past my fat finger, sorry about that. But effectively everything in red here is the second turn of that Ferris wheel. And as we continue and make more and more turns, and it kind of seems ridiculous to be graphing your height on a function table from the context of a math class, but realistically, this is just an application of something that we could do to see something that is continually on the same cycle, something that's repeating itself over and over again. And graphs are just used to analyze it, to see that in a more visual way. Every single time we get another turn, it's basically going to be a repetition of that very same period, that very same curve there from start to finish for 360-degree intervals. So they ask us to describe it, and it would be in just really kind of improper English or short non-formatted English. How would it be similar to the problem in problem 5? It would be the same curve, just repeated. So it's a repetition, it is a cycle, it is a full revolution, kind of thinking about it like such. All right, last problem here on this page. Describe how the function in problem 5 would change if the Ferris wheel had a diameter of 60 feet. Well, naturally, if our Ferris wheel didn't have a diameter of 40 feet, but now 60 feet, the only thing that would change is that our heights would obviously be higher or lower. We know that we're still starting 2 feet above the ground, but effectively, our starting point right here would now just be the radius of a 60-foot, circle, which, there we go, would now not be 20, but 30. So instead of, and making a really quick sketch of this here, instead of having heights of 2, 22, and 42 on this curve that we saw on problem 5, which again looked a little something like this, at 0, 90, 180, 270, and 360 respectively. And again, sorry for the really quick chicken scratch, trying to do this real fast on my iPad. All that would change now is instead of having 20-foot increments going up 20 or down 20, well, now we would have 30-foot increments. So our values, our highest point would be 62, and then our lowest point would still be 2, because you can't go lower than the lowest value on that. It's just our starting point wouldn't be 22 anymore, it would be 32. So basically, the highest point would change and the starting point would change. Kind of to summarize it really efficiently. The highest and starting points would change. And they would actually increase. All right. Hey, that's the hard part of today's lesson, at least in the sense of lesson 8, because that was, again, kind of a review, and I really wanted to, I moved past that on Tuesday so that way we could see Sokoto right as we were finishing up. But I wanted to come back and finish these problems, not just for the sake of hearing this explained to you in person and kind of getting a little bit more insight as to why the answers are what they are in the PDF answer key I put up, but also really to review this idea that something that is circular, or a unit circle, can be unhinged, snipped, so to speak, and then spread out like a string in a wave-like motion. And all of our sine and cosine functions, as we'll see on the next lesson, in about the next 10 minutes for the remainder of this class, are wave-like motions, and they have amplitudes, heights, and certain areas that say what we call a period, a relative measurement from start to end of one full cycle. All right, last problem on this homework is a review problem, number 17. Diana spends 17 hours in a 2-week period practicing piano. How many hours does she practice in 7 weeks? Well, I can guarantee you that if she gets 17 hours in 2 weeks, it's going to be more in 7 weeks. And there's many different ways to solve this. Since the problem itself, or the review itself, is calling on our beloved proportions, flashback to previous math classes, keep in mind proportions are basically situations where you have fraction equals fraction. It's an equation of fraction. That's what a proportion is effectively. So what I'm going to do is I'm going to create a proportion and say, all right, let's create a proportion actually like as follows, and let's talk about hours relative to weeks. If any of you work, I'm sure you are very familiar with this. You probably don't write it in this form, but like 40 hours a week, 20 hours a week if you're part-time, et cetera, et cetera. That's the proportion, or the ratio, comparison by division, that I'm going to make. So now I'm going to fill in the blanks. All right, hours per week, 17 hours per 2 weeks is equal to how many hours? Well, we're staying consistent, hours in our numerator. That's what we're looking for, so I'll call hours H per 7 weeks, boom. And again, this is just the proportion way of solving it. What y'all might have done is you might have done this, say 17 divided by 2, you realize that, oh, on average, she practiced 8.5 hours per week, and then taken that number and turned right around and multiplied it by 7. And theoretically, this process over here, if you did that mentally or with a calculator, is synonymous or the same thing as what we're about to do. When we learned proportions in previous math classes, I don't know how your teacher taught it to you, but effectively, one of the main strategies is cross multiplication. And cross multiplication is just an application of isolating a variable. And that is basically what we did over here. They just don't typically explain it as such. Or maybe they did, I don't know. But here we go. 2 times h equals 7 times 17. That's the cross multiplication. 2 times h equals 7 times 17. Let me scrunch the other way of thinking about it. I like the logical way over here too in the blue personally. But then we would realize, hey, to get rid of the 2 in front of the h, we would divide by 2. And now we just have h isolated. And it's almost like what we did over here in blue is already done. We divided 17 by 2. And we took that answer and multiplied it by 7. Boom. Either way that we get it, we are going to figure out with a little bit of arithmetic now, with a little bit of calculator work, that 8.5, aka 17 divided by 2 times 7 is, I'm just going to work it out over here. The amount of time that Diana would spend in 7 weeks is 59.5, and we know we always label because we're good mathematicians and good students. Boom, hours. Dang, Diana, committed. Respect that. All right, so that is our solution. Wrapping up lesson 8. Let's go rapid fire into lesson 9 since we have 8 minutes left. I don't want to waste y'all's time. I do appreciate y'all being here. Very, very much. Y'all know that. Hopefully you kind of get that vibe from me every single time you're here, because I really do appreciate y'all's participation. And also, as I'm transitioning to lesson 9, I know some of you couldn't be here today because of AP tests. Best of luck to you. I hope you're crushing it right now as we speak. All right, lesson 9. Again, you don't have the text in front of you because we don't have it tangibly, meaning you don't have it in your hand, but hopefully y'all can find it on the Google Classroom. We know it's posted. This is on page 141. It's our lesson summary, seeing that we can take a circle and unhinge it and turn it into a wave-like motion on the coordinate plane, y and x-axis. So here we go. Number 1, changing the graph of sine of x. If degrees are changed to radians, then 1 period, and by the way, a period, what it says right here in the directions, is basically a full rotation from start to finish. This is a period of that graph. Synonymously, flashback to the Ferris wheel example, 1 period of a Ferris wheel is 1 full rotation, 1 trip around it. So 1 period of the graph y equals sine of x is shown here. And now we want to fill in the missing radian measures. So effectively what we're trying to do here is realize, what is the radian measure when sine of x has a y value, a height of 1? Remember, sine is always y. That's why I actually wrote that there. So on our unit circle, where do we have a height of 1 for sine? It would have been efficient for me to actually have copy and pasted this, so my apologies there. But I'll bring it back to one that we do have copy and pasted. Sorry if this is killing your eyesight. There we go. Bless you. Here's our unit circle. Let me copy and paste this thing now. Oh gosh, didn't really quite do what I wanted it to do. All right, so hopefully you don't have issues with moving screens back and forth, but where is our height 1? Boom, right there. What's our radian measure? Pi over 2. So as I go back over here, a little bit of quick memory, short-term memory skills to the max. Where do we have a height of 1? Pi over 2. Sweet. Where do we have a height of 0 after pi over 2? Well, notice basically there's only 4 boxes here, so I can think of this as fourths, aka quadrants, aka 90-degree angles. So a little bit of manipulation of previous conversation helps us understand that. And that's going to be at 180 degrees or pi. Where do we have a height at -1? Where's our y -1? Oh, look at that. And what's that radian? 3 pi over 2. So now again, we're just writing radians down here, saying, all right, what's the radian measure to get us these y values? And last but not least, where do we get back to a height of 0? Well, that's a full circle. That's 180 degrees past pi, which is 180 past 180, or 2 pi, a full 360 degrees. There is 141. All we were doing was relating the unit circle, and I'm sorry for bouncing back and forth between lesson 8 and lesson 9 here. The unit circle here, looking for the y values, the signs, and then dropping in the related radian measures, distances around the circle to that value. All right, progress being made, cruising on down. Stop me if I'm going too fast. I'm trying to help you out since we only have 4 minutes left. I want to try to get us through this. We have the sine function here, by the way. It's the same thing as what we were just looking at, which is awesome. But now instead of measuring these values in radians, notice that, excuse me, all of these x values are not radians, like pi over 2, pi, 3 pi over 2, and 2 pi, but rather they're now degrees. And notice we expand beyond just one period. This is one period or one start to finish. Like a period in a sentence tells you where the sentence finishes, and the next sentence begins. This period graph, this full rotation of a graph, extends beyond it to the left and to the right, because theoretically something in motion can continue in motion. We just normally focus on the first rotation when we're starting to learn the unit circle. So long story short, that's a lot of backstory. We want to use this graph here to our advantage, and let's see if we can do so. Desmond is trying to determine the value of sine of 45. See if we can help Desmond out. He decides that since sine of 45 is halfway between 0 and 90, well then sine of 45 probably should just be half of the height at 90. Well, that's theoretically logical. We actually unfortunately know that that's not true. So sorry, Desmond. The value of sine of 45 is, by the way, it's root 2 over 2. All I'm going to do, and by root 2 over 2 is approximately 0.71. I don't care about that value. I just want to use this graph to show that he's incorrect. So what I'm going to do is I'm going to go halfway between 0 and 90. And here's how I'm going to do it. I'm going to count the distances. Ready? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So basically there's 9 values across the x-axis, allowing me to think that, hey, this x-axis is going up by tens. Okay. All the way to 90. Let me zoom in a little bit better because it's really hard for my fingers to write that. Fine motor skill is not my specialty. So we have tens across the x-axis, which lends me to believe that my 45-degree angle is probably going to be right here, halfway between 40 and 50. So all I'm going to do now is I'm going to extend that up as straight as I possibly can to right about there and see if it's at 50 or 1/2 of 1. Well, here is 1. Here is 0 on the x-axis, which would lend me to believe that that's the halfway point. And sure enough, let me use a different color here. If I extend this over, is this height right here at that height? Well, obviously not. So we can see that Desmond is incorrect because the curve at 45 degrees, and keep in mind, y'all, we kind of estimated this by counting. We said that's 45 degrees. But whether it was either slightly bit to the left or to the right, obviously that right there is way higher than the half. So the curve at 45 degrees is above the value of 1/2 on the y-axis. And this may be our final go for today. Okay. Using the graph, clear out all of this unnecessary writing. Okay, get all this off. Here we go. Using the graph up here, we're going to determine whether sine 250 is greater than, less than, or equal to sine 290. Let's do this rapid fire. Here we go. So 250. So here's 270. So I'm just going to use basis of comparison. Okay, so 250 is going to be represented here in green. Boom. 290 is going to be 2 to the right of it. Boom. So I'm going to cruise on down to my graph. My points. Are these 2 points at the same height, or is one taller than the other? And the answer is they seem to be at the same height. Okay. I'm going to go to 25 and 85. 85 on my graph, super close to 90, like right there. Okay. 25, way over here, like right there. So I think it's quite apparent which one's higher. Is that one. My 85-degree angle is the value of the y at an 85-degree angle is definitely bigger than the 25-degree angle. And last but not least, 140 and 160. It's the final countdown. Here we go. Which one's bigger? Where's the height at 160? Well, here's 180. So 170, 160 would be here. That would be the height at 160. I don't actually care what its real numerical value is. Here's 150 and 140. So obviously which one is higher up, which one's taller? Well, sine of 140. All right, y'all. That's going to wrap it up for today. I appreciate participation on that one answer. I know I threw kind of a curveball at you asking y'all to participate in that, but I do appreciate it. And I very much appreciate, going to throw that word out a lot right now, y'all being here. Keep filling out those forms. Keep hitting me up with emails. Y'all are doing a great job. And I respect and truly enjoy having y'all in class, even though it's definitely not as fun as when we were in school. So let me know if you have any questions. If not, have fun, be safe, have a great weekend, and I will hopefully see y'all next Tuesday when we finish up this year in trigonometry. Bye, everybody.
Thank you.
You're welcome.
Thank you.
Thank you all for joining. I appreciate it. Stay safe. Take care.